Hello everyone and welcome to a very quick video where today I found a video by Anthony Baer that was only very recently released, and it is genuinely one of the most funny and baffling misunderstandings about physics I've seen in a long time from the flat earth crowd. And in addition, it carries the taboo conspiracy seal of approval, so you know it's going to be very funny. um, I love how he says, "Oh, the globe propagandists will now throw some fairy dust and word salad," but I will actually, use physics, the thing that you clearly have no grasp upon. But before I go too much into detail, I would like to show you what we're dealing with today.
Let's say you're walking on the equator, and of course, the Earth is spinning. Now, do you know when you're traveling in a circle, you're spinning in a circle, you're accelerating?
Yes, you are indeed accelerating. That is correct, dear Anthony. However, when you're traveling in a circle, the forces of acceleration. Now, this is with if you yourself were holding some sort of string and you had a ball at the end of it, there would be a centripetal force inwards from the string and the centrifugal force outwards. Notice if you are in uh, constant rotation or constant circular movement, that there is no force applied either in the direction the ball is moving or in the other direction. This is extremely crucial and very basic in physics. The centrifugal and centripetal forces are outward. Uh, so you could say they are orthogonal to the path of inertia as is depicted here. If you'd cut that string right this instance, the ball would go on moving that way. And so it's a tangent, if you will, to the circle of motion that you have in this sense. And the centrifugal force goes outwards. Showing footage here from the rotating chair for astronaut training
But if you were on the equator
or pilot training.
and the Earth was spinning, would you feel it?
No, you would not.
Whoa.
That's because the force at the equator that would be outwards, first of all, would be a constant force. So, no, you cannot feel a force in the sense that it is overlapped with gravity, such that you would still just be pulled to the ground just a tiny bit less than you would be, for example, at the poles, right? But because the change is very slight and your body can acclimate to it, you will not notice it essentially.
Whoa.
Also, it's about only a percent or so of gravitational attraction at the equator.
Let's take a look. So let's calculate how fast the Earth would be accelerating if it was spinning. So if something's moving in a circle,
And that formula is correct. He uses the formula v squared divided by r, which is completely correct. And he just asks AI a whole bunch of stuff. I mean, those calculations you could really do yourself. I'm unsure why you need to use a whole bunch of online tools for that and ask AI twice, but okay. The numbers are correct, right? The centripetal, or in this case it's centrifugal, but the formula is the same anyway. Acceleration would be 1.33 inches per second squared. Now, because I am in Europe, I have zero idea what this unit means, and I've since found out that it is roughly 0.033 meters per second squared, of course. Because I only got inches per second to meters per second because, I don't know. Does it do acceleration? I don't think it does. Yeah, no, it doesn't. But it's the same conversion factor because the second is the same. You only need to convert from inch to meter, regardless. um, that's less than 1/100th. That's about 3,000ths, 4,000ths maybe of the gravitational attraction at the equator, which you would not feel. So technically, you could end the discussion already right here. But now come, and this is an argument the flat earthers have made countless times of, oh, you would feel the Earth. You really wouldn't, for the reasons I gave. But now comes the hilariously misunderstand part.
okay, we got our little accelerator machine, got a big long arm for leverage. and then we're going to use it to accelerate something or somebody. This is the accelerometer part of our machine. So we have marks 1 through 5 seconds, so we can use those to match our calculated
Because 2 seconds are clearly overrated.
speed of the Earth. The distance per second is not linear because the calculation is squared. So you can see here at 1 inch, obviously we're at 1.33
Yes, this is how acceleration works.
inches. And then at 3 seconds, we're at 5.9 inches.
Now, I did not cross-check the rest of these numbers there, so but I regardless, he's completely missing the point.
And at 5 seconds, we're at 16.6 backwards dramatically.
Because he's now
in
letting
order
someone
to keep a constant acceleration. You're standing on
stand on this
the
metal
Earth
plate.
backwards. Here on the equator, we're going to accelerate the same as the Earth would accelerate. It was spinning.
And he's moving
So this is going to be a 5-second deal. Ready?
them backwards now. And that's the funny part, because if you were walking on the equator, the force would not go in the tangential plane that you're moving in. It would go upwards. That's the thing that bothers me so much. Flat Earthers continuously fail to understand the globe model. No wonder they disagree with it. This would be stupid. This is not how this works. Anthony, please, I cannot emphasize this enough. The acceleration would be upwards. It is upwards at the equator, I should say better. You can actually measure that with scales, with precision scales. You can measure that. Bob the Science Guy did a video, and what's his name? Critical Think, I think, also did that.
Did you feel it?
Yes.
The whole time?
The entire time.
Unsurprisingly, because, and that's the thing, you also, not only is that not how this works, she was also stationary at first. Then you started moving her. When you, this centrifugal force that you're talking about and that you have calculated would be upwards, but the total system would be stationary. That's the thing that gets me. You're asking to, at best, at the very, very best, let a human feel 3,000ths of the normal gravitational attraction that pulls you towards the ground in difference. At the best. And even if you could teleport someone from, say, the North Pole to the equator, they may still not be able to feel it because it's such a small change. And the fact that if you go to the equator, your travel there is not instantaneous, makes your body adjust to this difference. This is ridiculous.
Spinning. So this is going to be a 5-second deal. Ready? I'm going to tell you when we're ready. We're just going to go.
I love it. This is amazing. It baffles me. Again, here is even part of your formula. The force that would actually be applied, and mass, just for you, Anthony, the mass would not change the direction here. The force, the acceleration would also go outwards for centrifugal force, and inwards if you also calculate the force that's keeping our hypothetical ball in this example close. But that's not what we're talking about. We're just watching centrifugal force. It would also go outwards. The acceleration would go outwards. My God. I don't know what to say. I'm baffled.
Did you feel it?
Yes.
The whole time?
The entire time.
And
That
it goes
makes
on
sense
like
'cause you're
that.
top heavy when you're standing.
He keeps going on with a chair. Amazing.
According to our results, it doesn't look good for the globe. Now,
Oh my God. It doesn't look good for the globe because you have completely misunderstood it. This is what you do, at least what you do in Austria, when you're 14 or 15 in it's fifth grade in secondary school. So it's like ninth grade, maybe in the US or wherever you are from.
we tried it with another person, and we got the same results.
Oh, big surprise.
Now, don't remember when you're traveling in a circle, you're accelerating, so you can't.
Yes, but you're accelerating outwards. If you were standing here in Central America, the force from rotation would point this way, outwards, not in the direction that you're moving. because otherwise you accelerate while literally not moving.
I just say,
Oh
oh, I
my
don't feel it
God.
because of gravity. It doesn't work that way.
Yeah,
Okay.
no, it doesn't work that way. Is completely correct. You don't feel it because it is only, as I said, like 3 thousandths of the force that you'd normally feel pushing you downwards difference. You're just 3 thousandths roughly lighter at the equator. Only 3 thousandths.
Okay, let's borrow a dog and try it.
I'm sure the dog will also feel
He's
it
like, whoa.
if you apply it this way.
Yeah. Even at half speed, it's not looking too good. Okay, I'm gonna try to move as slow as I can.
This is amazing.
It's not moving, and you drop it. It's gonna follow the level straight down. Yay! So you should be able to go to the equator, set up a level, and if the Earth was spinning and you
Dude.
drop it, it should move away from the level. But I guarantee you that's
No, it should not, because it is moving with the Earth. It is moving with the Earth, and the Earth has a constant rate, a constant angular velocity. So it has the momentum required to land precisely in the same. It moves with the Earth because it has its momentum conserved. This is appalling. This is horribly poor understood. And the fact this makes it so much funnier that Taboo Conspiracy was like, yeah, this is amazing. Wow.
not going to happen. Which brings me to another point. I can understand the theory of gravity holding the air to the Earth, but the Earth is
Which, to be fair, you have a leg up on most flat earthers then.
spinning. That means it's accelerating, like I showed you.
But it is accelerating out from the center.
If it's accelerating, wouldn't the air fall behind like the ball?
I think we're done here. I think that's it. No, I don't want to talk about this anymore. This is ridiculous. I hope I can see you in the next video. Until then, I wish you a nice time. If you enjoyed this video a lot, maybe consider subscribing. And if you enjoyed it a lot, maybe consider subscribing and leaving a like. And I will see you in the next video. Until then, goodbye.